Anyway, regarding today's webinar, we've got Peter Hughes with us, who's a principal researcher at the University of Huddersfield. And Peter has got a lot of experience of rail in the UK and Australia, and he will be doing a presentation on, as it says here, improving railway safety with state-of-the-art text analysis. We're going to end with a Q&A session. So when we get to that, if you've got questions for Peter, if you type them into the questions box on GoToWebinar, I'll be asking them on your behalf. So over to you, Peter.
Excellent. Thank you, Julian. So as Julian said, yes, I'm a researcher at the University of Huddersfield. I've been researching railway safety and in particular text analysis for railway safety for the past 6 years. As we say, the presentation today, improving railway safety with state-of-the-art text analysis. I've split the presentation into 2 parts. The first part, I'm going to describe to you the problems we were given, the approach we took to solving the problems, and the results we obtained. The second part of the presentation, I'm going to speak a little more broadly about NLP, natural language processing, and some of the discussions you might see in the press releases about NLP techniques. What we found from looking into those techniques and where we're going in the future with our own research. So I have 20 slides overall. So if you're counting in the presentation, we're on slide 2. I'm going to start now with talking about the research that we've done, the problems we were given, and the results we found. So I'll talk about 2 example problems we were given. The first one is to obtain information from close call data. The close call database, it's a database that the railway in Britain has. It allows railway workers to report hazards. So it's not an accident database. It doesn't talk about events that led to injury or damage. It records hazards. Things that might lead to injury or damage, but they're problems that need to be fixed now to stop accidents happening. The close call database is available to railway workers. They can enter any text they want. There's no, there are some constrained text fields, but the core data we're looking at is the free text that railway workers can enter. Records can be entered into the database using a mobile phone app, by emailing the record in, or by telephoning, speaking to a telephonist who then records the information from the railway workers. Because this is a large database of safety information, what the railway wants to be able to do is get the information, get the trends, identify what's going on in the railway, identify what hazards there are, so that they can put in place the mitigations to improve the safety, to stop the accidents before they happen. The close call database has more than 1 million records in it. That's more than 1 million free text records in it. And there on the right-hand side of the screen, those are genuine examples of text from the close call database. So just looking at the first one, disregarded oil canister. What it says there, BEJ 18 miles, 880 yards. That's a code that's used to explain a very specific location on the railway, which I looked up earlier. That's somewhere in Derbyshire, as it happens. Disregarded oil canister. Well, it doesn't matter that nobody's looking at it. The point is it's a discarded oil canister, but the person writing that maybe had autocorrect, or maybe had the wrong word in their mind. But what we're saying is there's a hazard on the railway, in the railway corridor, an oil canister that shouldn't be there. Next one, for example, loose debris remaining in service holes. There you go, someone had trouble with their spacebar. Now that's something that we can see from looking at that. We know that loose debris is 2 words. We know that in service is 2 words. We as humans can read that. We can probably understand what was meant by that record when that worker entered that text. Can we get software to do the same? Going down, the fourth one, banded teram looks unstable. I don't know what that is. I don't know what a banded teram is. The person who entered that text does. Probably other railway workers do. Me reading that, I don't know what that means. Can we get software to find out? That's the challenge we're given. We're also going to look at the sixth record we've got here, access gate left open. That is the single most commonly occurring text record we have in the database, access gate left open. That's something many workers want to tell us about, which when you look at it, it's quite clear, it's quite simple what it means. Of course, access gate is a tautology. All gates are access gates. If it's a gate you can't use for access, it's a fence. These are typical of the records we've got. We've got 1 million of these. Can we get software to somehow read these 1 million records? Because we can't get a person to read those 1 million records. The person would tire, the person would make mistakes. If we had a team of people reading them and working together, they'd have different interpretations. What we were asked was, can we get software to read these records and give us an overview of safety hazards on the railway? That was the first challenge we were given. The second challenge we were given was interesting for a whole lot of different reasons. The Swiss Federal Office of Transport has, like all transport departments, like all railways, records accident reports. There are 4 official languages in Switzerland. The 3 that are commonly spoken are German, French, and Italian. And accident records in that database are recorded in 3 different languages. We were given a database of more than 5,000 records, and we were given 5 categories of incident. And we were asked, can you get software to read these text reports in 3 different languages? And can you get the software to categorize those records into those 5 categories of injuries occurring whilst passengers were boarding trains, whilst they were alighting from trains, injuries from public and passengers falling downstairs, struck by closing doors, that's train doors, or struck by falling objects. So those were the 2 challenges we were given. And we then set out to see if we can solve those problems. So how do you solve those problems? Well, when you start researching, you find that there are a large number of natural language processing methods. And very conveniently, there are a large number of code libraries and packages you can use. And many of the tools are free to use. So there on the bottom right of the screen, that's just a medley of logos, but many of those natural language processing tools and packages are free to use. You simply download them and use them. What are natural language processing methods? Well, there are many of them. I've got some dot points here on the top right of the screen. When I was preparing this presentation, I actually started listing these out in detail and giving each of those methods a slide to itself. What I found was I was actually writing a 10-week lecture course, and I was going into lots of detail. The trouble is, some of these methods you can't describe simply and quickly because that leads to more questions than it gives answers to. So instead, I'm afraid I've given them here as dot points, which I'll run through very quickly. Automated spelling correction, we all know what that is. We all see it when we're typing text messages, in particular mobile phones often will either change a word if it believes it's being spelled incorrectly, or it will provide suggested alternatives. We looked at automated spelling correction tools for our text, and as you can see in the earlier slides, you could see there was definitely some non-standard spelling in there. We looked at automated spelling correction tools. We found that On average, we were getting something between 40% and 60% accuracy from those tools. So what we're finding was in some cases, those tools were getting it wrong more often than they were getting it right. In many cases with specific railway terms, the automated tools were changing words that were spelled correctly as far as the person entering the text was concerned. That term was spelled exactly correctly, but the automated spelling tools were corrupting it into something that wasn't intended. Instead, we built our own dictionary, and I'll talk a little in a bit about how we went through that process. We built our own dictionary, and then we used these tools. The Levenstein distance, that's a spelling distance. So if you have two words that are spelled similarly but not exactly the same, it gives you a measure for how far away those two words are in their spelling. So the words cat and cap are quite similar, whereas the word cat and dog are much further apart in spelling distance. Soundex similarity, that's another measure of distance between two words, but based not on the spelling, but on the phonetics of those words. And that one is very useful, particularly on the railway. There's a certain type of plant on the railway. It's an introduced pest. It occurs a lot along the railway corridor. It's a buddleia, the butterfly bush, buddleia. Nobody knows how to spell buddleia. I looked, the Oxford English Dictionary gives two alternative spellings for the word buddleia. One has an H in it, one has a J in it. Nobody knows how to spell the word buddleia. We in our database have more than 50 different spelling variants of the word buddleia. Detecting those spelling variations from spelling distance alone, we could do that, but we're finding some quite large distances. The Soundex similarity, the similarity of phonetics, was very useful for that. Moving on now, regular expressions. You may be familiar with regex. It's a pattern matching tool for text. It's very powerful, although quite difficult to use sometimes. That regular expressions are very useful when you're looking for codes. So as I showed you earlier, we had that code of BEJ, 18 miles, 880 yards. That has a standard form. We have a 3-letter code, and then we have a number of miles and a number of yards. We can use regular expressions, regex, to find those patterns. Part of speech tagging and chunking. If you went to high school in the United States, you'll be familiar with this. It's called sentence trees. Can we identify the nouns in a sentence? Can we identify the verbs and the adjectives? Can we join them together to say this is a noun phrase, this is a verb phrase, this is the main subject? Can we identify the words that are the doing words in the sentence and the words that are the naming words? We looked at that, and I personally tried over and over again to get part of speech tagging working. The trouble is, the part of speech parser I was using was about 80% accurate per word, which, if you work it out for a 20-word sentence, means that you get about 1% accuracy for the sentence. Over and over again, I tried different methods of using the part of speech tagger and the chunker, and eventually I had to give it up. Lemmatization is reducing verbs down to their base form. So the word jumped is reduced down to its base form of jump. Jumping is also reduced down to jump. So truncating verbs down to their base form. Lemmatization is a very useful tool for finding sentences that are talking about the similar activities, even though the part of speech, the conjugation of the verb might be different. Interestingly, English, yes, there are some irregular verbs that have different endings. Of course, be, am, you are, we are, he is. They're all non-standard forms. They don't follow the normal rules. English only has a small number of irregular verbs, and it's quite easy, in fact, to to list all of those out and build those rules for those irregular verbs. Lemmatization works very well. TF-IDF is term frequency inverse document frequency. It's a method of providing a score to each individual word in a document. The score is based on the apparent importance of that word. We found TF-IDF works very well for us for picking out important words within a document or within a sentence. Next two methods, LDA and LSA, they have seemingly similar names. They're very different techniques. They're mathematical techniques that try to look at individual words and try to provide some categorization of documents or sentences based on the words within the sentence. They're heavyweight mathematical techniques, and I couldn't get either of them to produce useful results for me. A very interesting finding, however, with latent Dirichlet allocation, a colleague of mine researching in Finland found that she got good results with LDA for Finnish text, but not for English text. I have my own hypothesis as to why that might be the case. But what I can tell you is myself and other researchers can't get useful results using LDA in English. Finally on my list there, Word2Vec, that's software, you may well have heard about that. That's a tool made freely available by Google that uses a shallow neural network. It's got some hidden magic going on inside it, but it does produce very good results. So that's an overview of the methods we looked at. Okay, that's a lot of methods. What do you do with those methods? I could sit here and list lots of methods, and like I say, I could give a full lecture course. I could give over a lecture to basically each of those methods. That's not that interesting when you're trying to get information from the text. The question is, can you use them? How do you use them? How do you put them together to get the results you want? If you look in the literature, there's a lot of talk about pipelines. It says there, the consistent advice is to use the available methods in sequence to create a pipeline of methods, one method, then another method, then another method, and hopefully you'll get useful results at the end. However, when you look at the literature, you find that there is no consistent pipeline agreed on. And these, what I have there on the screen, these are just 4 random screen grabs I've taken of pipelines that people have proposed, and they're all different. No one can agree on how you should use natural language processing techniques in order to get the results you need. And probably in there you'll find some people talking about natural language processing methods that I haven't been able to get working for me. So that's what doesn't work. What does work? Overview of our approach. What did we do? We started by storing our data in a graph database, and we created separate nodes in the graph database for records, sentences, and words. We have a lot of fun. In fact, with most of our work, we're using graph databases. We find them very useful for a number of reasons. We then used a semi-automated process to identify key terms. So this was the TF-IDF process, basically, that I was talking about earlier. We adapted the method to work for n-grams. N-grams, you might know them as compound nouns. It's where you have more than one word to describe a single object. So, for example, level crossing. The term level crossing appears a lot in our data. That's 2 words, level crossing. It's one thing. It's a level crossing. Network rail. That's 2 words, but it's one organization. British Transport Police, the same. So when you're looking for relevant words in your data, you're actually looking for relevant terms. A lot of the terms you're looking for are made up of more than one word. We use the TF-IDF method to examine the data to find the apparently relevant terms. So we adapted the method there to work for n-grams. Once we found terms that were relevant within the text, we used the spelling variation tools, so the Levenstein distance, the Soundex similarity tools, to look for words that were seemingly similar. And again, went through a manual process. We used the software to detect the candidates' similar terms, and then had a human analyst go through and check one by one. You might think that we could automate that process. Surely the top 20 words in any list would be correct spelling variations. So we could always take the top 20% of terms in any list. No. Often you might find a word, you'll look for words that appear to be similar based on spelling or phonetics, and you might find, yes, the top word on the list is a spelling variant of the first word. The second one, no. Third one, no. Fourth one, yes. English is so varied in its spelling, in its usage, that you can't use automated tools to detect spelling variations. We found that we had to go through manually. We could get the software to find candidate spelling variations, but we always needed a human in there. Once we detected terms that were relevant to what we were looking for in the database, we then created a knowledge graph of those terms, and I'll speak a little more about that on the next slide. We started linking objects together. As well as the words, the sentences, and the records in the database, we created a knowledge graph, a model of the real world. How do these different objects in the world interrelate to each other? Having created the knowledge graph, that gave us different areas of safety risk management for us to look at. They gave us different core terms that we then used as search terms. We went back into the database with those search terms and said, what terms are spelled like these? What other terms occur in records along with these terms? I'll show you this in an example on the next slide. We used an iterative process of the NLP methods and the human interaction to look at the data, sort through the data, create a knowledge graph, use the knowledge graph to then direct our next searches back into the data. The knowledge graph is key to obtaining information from text data. Knowledge graph shows relationships between objects in the real world. I'm certain I'm telling you what you already know. If you've done a computer science degree, I'm sure you're familiar with knowledge graphs. On the right-hand side of the screen there, that's an actual example of a part of the knowledge graph that was used for our analysis of railway safety. Looking from the bottom, working upwards, nettle is a term that's used in the database for stinging nettle. Stinging nettle is also a term that's used for stinging nettle. There might be other terms that people use for stinging nettle. Stinging nettle is a type of plant. In the database, we had a number of types of plants. I think we had trees, bushes. Stinging nettle was categorized as other plant. It's not a tree, it's not a bush, it's categorized in our database as other plant. Plants have different parts. They have stems, leaves, foliage. These are all terms that appear in our database. In our knowledge graph, we link the terms together. So we use the knowledge graph to make sense of the words that are appearing in the database. The huge advantage we got from using a graph database is that we could have the database of text, of records, sentences, words in the exact same database as we recorded the knowledge graph. We could actually link the words that were occurring in the text with the terms that describe the elements that appear in the knowledge graph. This was extremely useful because then what it meant was we could look in the knowledge graph and say, I'm interested in plants, particularly plants that aren't trees or bushes, so let's say other plant, and I want to find records that are related to that type of plant. We could start our queries from the knowledge graph And because the knowledge graph was linked to the words, to the sentences, to the records, we could then go back into the database and find the records we were looking for. The knowledge graph is a key part of our research. And the other picture there, the picture here with the colored bubbles in it, that's showing an overview. This is the metagraph of our graph database. It shows that we had records. Records contain sentences which contain words. Words form the terms. And this is actually taken from our study of Swiss text. We had terms in 3 different languages, but it doesn't matter what language the term was written in. In the real world, the object is the same. In the real world, it's a train. You can call it a train or a zug or what you can call it a train. You can call it whatever. It doesn't change what it is in the real world. When people write text, they might write in French, in German, but what they are wanting to do is explain meaning about the real world. Using the knowledge graph, we were able to go from the records in our database to what the meaning was in the real world. And down here in the bottom left, I've just got a reference there to a paper in which we describe that in lots and lots of boring academic detail. So our process, iterative semi-automated process, a consistent finding from our work is that you can't leave the NLP processes alone to get meaningful results. Manual review is required at all stages. Process we used was interactive between humans and software. Software is excellent at searching quickly through large volumes of data, and it can use pattern matching tools to find candidate terms, but it's the human who knows about the real world. And we can use the software to present results to a human analyst, but the human analyst has to look and understand and judge that information to then build that back into the knowledge graph. The accuracy varies depending on the purpose of the analysis, and let me tell you of our results. 3 different tasks I'm talking about here. First one, can we categorize new records into an existing categorization scheme with examples? Yes, we can. Manual process had good accuracy for selected cases. In particular, the vegetation example I gave you, we were getting very high accuracy. In other cases, other use cases, particularly where we were talking about train safety and track work, we were getting lower accuracy, even though we were using the exact same methods. Developed our own in-house software in a number of cases. Second case here, categorizing new records into a known scheme but without examples. This is what we were asked to do with the text from Switzerland. Yes, we could do that. It was a labor-intensive process, but we got extremely good accuracy despite the fact that the records were written in 3 different languages. A third task we were given, can we infer meaningful categories from text without examples? Basically, here's a lot of close call records. Tell us, what are the categories that are in here? What are the groups of things that people are trying to tell us? That was a very labor-intensive process using incremental learning with software. Our accuracy varied somewhere between 68% and 97% compared with a human categorization, depending on the case, depending on the case study. And if you want better accuracy, you just put in more effort. It becomes more and more labor intensive. So, summary of our results. Can we obtain useful information? Yes, we can. The accuracy is varied. The accuracy depends on the data we're looking at, depends on the use case, and in some cases, the methods can be extremely labor intensive. For the trilingual text, we were able to obtain very high accuracy because the data were very well curated. There, the records were entered by professional text entry staff. It was their job to enter those records. We had low spelling variation. We actually found we had standard descriptions of accidents that we used, standard phrases. An elderly gentleman was found to have fallen down the stairs. The same phrases were appearing regardless of the language the text was written in. That did help our analysis quite a lot. So that's a summary of what we did. I'm going to finish now with a quick discussion of NLP and what NLP, natural language processing, might be in the future. What you might think we should have been doing, if you've been reading the press releases, if you've been reading the same press releases I've been reading, if you've been reading the literature in the popular media, in the newspapers, you might think that natural language processing is a solved problem. You might read all the press releases and think, yeah, it's basically done. You might be thinking that I was making my life hard for myself. You might be thinking, Pete, you should have just gone and done it with artificial intelligence. It's already done. You might think that. I wondered that. I went looking for the artificial intelligence that could do that for me. When you start looking behind the breathless headlines, you find that, in fact, the hype and the reality are very different. Let me give you two examples. You might be familiar with Google News. Google News, it's a Google tool, it's a news aggregator, it's online, it's available to use right now. Their graphic, that's a screen grab I made this morning of Google News. What you can see it's doing, it's picking up a theme it's identified in the news, and it groups news articles from different sources, from The Guardian, from the BBC, from the Times, and it groups them all together for me to go and look at them. It then finds a different topic and it groups articles from different sources there. It groups together news stories based on apparent category. That's good, but I still have to go and read all those articles myself. If I want to understand the different perspectives that are being given from The Guardian and from BBC and from the Times, I have to go and read those articles for myself. Well, surely that's the job of an artificial intelligence. If it's an artificial intelligence, it's intelligent enough to go and do that for me, but it can't do that for me. Now, Google make revenues of $160 billion every year, and they haven't found a way of getting an artificial intelligence to work for them, doing that probably fairly simple task. When it comes to reading those different sources and understanding the different perspectives, I still have to do that myself. Here's another example, using one of these Amazon tools. I had a conversation with one. Alexa, find me a recipe for peanut butter cake. Okay, said Alexa, I found you lots of recipes. Do you want me to read you one? Yes, please, I say. Alexa reads the recipes. I say, Alexa, I don't have any brown sugar. Can I use white sugar instead? Alexa says, I don't know. So what's the point? Where's the intelligence there? Yes, I can do a search online. I can search online. I can find hundreds of recipes. But when I want to understand the recipe, when I want to understand the different recipes, which recipes do use brown sugar, which do use white sugar, does it appear to be interchangeable between the recipes? There, I need the intelligence to go and look for me. At the moment, we don't have that technology available. And this is my own theory. Why not? Artificial intelligence, I never use the term artificial intelligence, but the artificial intelligence, what you might read about, you might read about how software has been used with, say, 100,000 artificial neurons and 10 million training examples and 1,000 hours of processing time. Perhaps we put all of Wikipedia into an artificial neural network and wanted to get understanding about the world. It doesn't work. It can't work. Humans learning language, it's a very complex process. Humans have 100 billion neurons in their brains. Now, they're not all given over to language acquisition. Many of them are given over to other functions. But within our brains, we have an innate ability to acquire language. All human cultures have verbal language. They don't all have written language, but any two humans left alone together will create a verbal means of communicating with each other. It's innate in humans, and we have 100 billion neurons in our brains, and many of them are given over to language skills. When we learn language, We get taught language from a very early age. I'm going to say hypothetically from, say, 2 years old. We're sat there with caregivers who say, look at the dog, look at the doggy, see the doggy. We're given repetition, we're given physical examples over and over again. We're out in the world with visceral feedback. If you've ever had kids, you'll be familiar with the conversation, don't do that, you'll hurt yourself. I said, don't do it. I told you that would happen. Even being told you'll hurt yourself, we go ahead and hurt ourselves. It takes that visceral feedback, it takes that pain, it takes that experience of the real world for us to understand natural language. And even a decade of learning every waking moment about the real world, about how people describe it with words. Let's say we start learning when we're 2 years old. Have a conversation with a 12-year-old. A decade of natural language learning doesn't create fluency. 12-year-olds are very good at natural language, but they're not fluent. Try speaking with a 12-year-old. Natural language is extremely difficult. Human language is written for humans to communicate with humans, and even we get it wrong. Even with a decade of experience, 100 billion neurons, and constant learning, we get it wrong. How can you expect 100,000 neurons with 10 million training examples to get it right? It can't. Natural language isn't like that. So finally, where are we going with our research? Unless software can make real-world inferences about the text, it will never be able to turn words into meaning, and it's an extremely difficult task. We are keeping the knowledge graph as a core part of our research. A lot of our research now, so our PhD researcher, Ryan, is looking at developing methods, possibly supervised or semi-supervised methods, so that the knowledge graph can be created from the text. Can we get a tool that can parse the text and create the knowledge graph itself, or create parts of the knowledge graph? And one of the challenges that Ryan's looking at, I'm just going to leave you with this example here that explains one of the problems with natural language. 2 sentences. The trophy doesn't fit in the suitcase because it's too big. Okay, yeah, that's very, very clear what that means. The trophy doesn't fit in the suitcase because it's too small. Well, that actually means the same thing. The trophy is too large to fit in the suitcase. In the first sentence, we've got the word it. We've got the word it, that's a pronoun. The pronoun refers to the trophy. The second sentence, we've got the word it, but we know now that the word it refers to the suitcase, because we know what fitting one thing inside another thing means. We've all done it. We've all tried to fit a thing inside another thing and found that it doesn't fit. Both of those sentences are easy for a human to read. Both of those sentences are the exact same words except for the very last word. Neither of those sentences is confusing. Humans can understand that. Can we get software to do the same? Because if we can't, we can't expect software to be able to perform general purpose natural language understanding. These are the challenges we've got. This is where our research is going right now. So hopefully I haven't run out of time. That's where we are. Our research continues. So that's not a picture of me. I don't look so sullen in my saggy bottom jeans or hoodie, but that's the long road we're going on our research. Thank you.
Great, thank you, Peter. That was a very clear, a very interesting presentation there. Very, very thought-provoking. So, question and answer time. I've got a couple of questions to start things off. If you've got questions you'd like to ask me to ask Peter on your behalf, if you could type them into the question box, I can then relay them and bring them together if appropriate to provide them to Peter. So first off, one of the things I was interested in was just your thoughts, Peter, around sort of semantic interpretation. Particularly when you come to 3-letter acronyms. So if, for example, you've used NLP, and in our discussion before the start of the presentation, there was both natural language processing and neuro-linguistic programming came in there. In the rail environment, you've got remote condition monitoring and reliability center maintenance, both actually quite close disciplines, but it's the same TLA. What are your thoughts on how we might be able to overcome those?
Yes, and another good example, member of the public, MOP. And in many of our close call records, it's simply written mop, which is an English word for something you use to clean with. But that's not how it generally gets used in the close call records, except sometimes it does. So someone might be talking about poor housekeeping and might be saying that the mop was left out. Yes, we might have the exact same word that has two different meanings. How do you parse that? As human readers, we generally can parse that without too much difficulty. And once you become familiar with the term MOP, you read records where it means member of the public, and you just read them. Your mind doesn't even have any pause whilst reading it, because our minds are able to train themselves to that. How would you do that with software? Our approach has been to try and look at the context around the term. So where the record was a mop was seen trespassing in the rail corridor. Trespass, that's not something that cleaning devices do. It's something that people do. People, member of the public, is a type of person. MOP is a term for member of the public, is a type of person. People can trespass. Cleaning devices can't trespass. So this is where we look for proximity on the knowledge graph. The terms, what the terms relate to, the objects on the knowledge graph that are being described by those terms, and then proximity on the knowledge graph to other terms that are appearing in the same sentence. Trespass and cleaning devices probably don't occur very close to each other on the knowledge graph. Trespass and people, member of public and person, appear close to each other. That's an approach we looked at, and it's an approach that has worked well in our examples that we've used for ourselves. It's not an approach we've got working automatically yet, but your synonym resolution, you've got a term that could mean to perhaps 3 or 4 different things. Which one does it mean? We've done toy experiments using proximity on the knowledge graph as the method of resolving that. We haven't got an automated method to do that.
Yeah, and I guess you'd have to feed in not just words, you'd have to feed in effect, all of Wikipedia plus a whole load of other things just to make that kind of thing work. So that'd be an interesting challenge there. Okay, so moving on, another thing I'd be interested in just getting your thoughts on. You talked about the processing pipeline and the fact that there are many different ways, that there's no one defined way, this is how you do the pipeline. So if you were to use different pipelines to process a batch of text, is a different pipeline going to affect the efficiency, the effectiveness of what you get out, or is it just not going to work?
Yes, it's uncertain, and I haven't. After reading the information on the pipelines and looking at them, and I was reading the pipelines thinking, okay, tell me which one I should be using, and there was no advice there. The pipelines describe processes and describe them very neatly. And from looking at the literature, you'd expect that you'd just be able to put in your text at one end of the pipeline and then go through each step and you get your results at the end. I don't believe that's possible. So to answer your question strictly, I think that if you use different pipelines, you'll just get different sets of wrong results. The only way we could get useful results was to have the manual intervention at each stage, the manual interaction and the iteration, repeating parts of the pipeline over and over again with the human going backward and forward. If we were to change the order of the pipeline, so our pipeline, which uses key term identification, uses the TF-IDF method, the key term identification, and then sorting those key terms putting them into the first cut of the knowledge graph, then looking for spelling variants around that. Well, we couldn't change we couldn't change the order of those two processes, because you can't look for spelling variants until you know what's the key term you're looking at the spelling variant for. We haven't tried messing around with the order of processes in the pipeline, but then I think I've abandoned the idea of traditional pipelines altogether, because I have not found that it's possible to just leave the processes to run through one by one, one after another. You always have to have the human interacting with the data.
So I think it sounds a bit like a conceptual one there, where you're using the tools as more decision support rather than being the automated tool that does everything for you. So it will do a stage, it does it for you quickly, and effectively you then evaluate what you've come through to then decide the next step. So so presumably therefore you'll need a fair amount of experience and knowledge from the people who are actually running the process.
Yes, and again, and I think that's true. So using the Google News example, Google News will be very highly automated. They have tens of thousands of news sources from around the world that they're scanning every minute of the day. There will be a very high degree of automation there. I imagine, I don't know what their methods are, but I imagine their software will highlight exceptional cases that need manual intervention. But I imagine a very large amount of that process is carried out as a completely automated method. They've got a completely automated method that has very good reliability for grouping news articles together. But still the decision, if I want to be able to interpret that information, that still needs the human. We can use the automated tools to do a part of the process, but the decision making, the inference of what that means for my real world case, we haven't got an automated tool to do that. Google might have one, but they're not making it available as part of their Google News service. The automated tools are very good. They're very fast. They can search very many cases very quickly, but they can't do, I haven't yet seen them do the automated decision making. That still requires a human.
Yeah, I think there's a dangerous step to take if you're not careful there. But actually, that leads on quite nicely to a question from Amanda, which I'll link in with a bit from me as well. So Amanda's sort of interested in, for all the close call records, whether there were multiple reports for the same incident, and therefore whether any analysis had been done about different phrasing or different ways of people describing the same incident. And the bit I would like to add on to that and just explore a bit further is based on, you may or may not have guessed, but based on my surname, I'm half Swiss, and knowing that Swiss German, so it's not just having 3 languages in Switzerland, Swiss German itself has a whole load of weird and wonderful dialects, some of which are not quite mutually incomprehensible to each other, but not far off it. Any thoughts there about those challenges around different ways that people will report the same thing?
Yes, I can't recall an instance I've identified in the close call database where I was certain that it was the exact one incident that had been reported by more than one person. Nevertheless, there are a large number of similar instances that get reported over and over again. Like I say, gates being left open. Workers being on site with the incorrect protective equipment. And there are common phrases that get used over and over again, particularly the shorter sentences, the shorter records. Ops on site with incorrect PPE. That's extremely common. That's an extremely common way for railway workers to talk. They have their own phrases, their own method of talking to each other. So that's a common way of talking. So again, we see that phrase appearing over and over again. But then we do see variants on that phrase. Ops on site without correct PPE means the same thing, but it's a slight change in the words. Yes, we then get a large number of different ways of phrasing the same description. I did look at techniques, and in fact, I was trying to use the regular expressions not for individual letters, which is how the regex was developed, but for words. I was trying to put tokens in and saying, if I've got a sentence that's built up of tokens for workers, which could be operative, which could be worker, on-site PPE, personal protective equipment, perhaps it's not the PPE in general, perhaps we're talking about ops on site with incorrect helmet, with incorrect gloves, without the correct gloves. So I was trying to use regex tools for putting in tokens and saying, well, if I've got this token and this token, doesn't matter which order they're on, you can have that token and that token in any order. I tried creating those. So I tried looking at examples in the text and saying, okay, I can write a rule that will match that example. And then I looked at another example. Yes, I can write a rule that matches those two examples. There were always different ways that people could invent to describe the same instance that I couldn't cover, and my rules were becoming more and more complicated, and I was finding that I was having to write more and more exceptions to the rule to pick up more and more edge cases, because I was doing it in regex anyway. In regex, it's fairly horrible and incomprehensible to read. If you haven't written regex, I don't believe you could ever understand someone else's regex. I had expressions that were ridiculous, that I had to abandon that approach. The number of ways that people think up to describe the same thing is beyond my imagination. I might be able to think of 20, and then real people out there in the world can think of 20,000 more.
Yeah, I think the 50 spellings of Budleer, I think, is also a good parallel description of that, or example of that. A couple of questions that work together quite neatly from Nikos Peter, really thinking about knowledge graph. So Nikos is interested in terms of the physical database itself, whether it's NoSQL or relational database. Peter was interested in terms of the process of building up the knowledge graph in terms of sort of common sense in the railway domain, and sort of how actually what's the workflow to actually come up with a knowledge graph that works.
Entirely manual. This was something we did struggle with, and we had one of our researchers was full-time building the knowledge graph, liaising with experienced railway workers. So the researcher who was doing that wasn't an experienced railway worker, was liaising with the experienced railway workers. The tool we used was the Neo4j graph database. So it's a NoSQL database, which, like I say, works well for us because you can build the structure of the knowledge graph directly in the nodes of the database. And because we've stored the text in the same database, we could actually link them directly to each other. The process of creating the knowledge graph was entirely manual, basically created from the researcher sitting with railway domain experts, drawing with pen on whiteboard to draw the bubbles by hand. The way you're describing it, this is one of these, this is a type of these, this is a part of this, drawing that on a whiteboard and then manually translating that back into the graph database. It wasn't an elegant process, it was a painful process. There's quite a lot of rework, and also, of course, when you make a mistake, you then have to go back and undo all the connections you've created in the graph database to then move an item and create new connections. It was laborious, it was tedious, and it was entirely manual. I would have really liked any sort of automated process there, but we didn't have one.
Yeah, I think that that's a reminder of the age-old thing that I try to remind people of. Anything to do with data and technology, having subject matter expertise involved is absolutely essential. You can't do it with just techies locked in a room. Which kind of links in neatly to another question from Amanda, where she's interested in the sort of the mixtures of, if you like, on the close call database of free text and slightly more structured data. Of trying to work out if there's an incident report, if you knew it was related to an incident, how you could then classify or maybe use slightly different rules to process the incident, maybe compared to a radiation-related issue, which isn't an incident. So was there a variation in the rules that are applied?
I'm sorry, my audio dropped out a little bit there then. Sorry,
Sorry, yes. So, yeah, try again. So in terms of whether the call related to an incident, would you apply a certain set of filters, a certain set of processes, compared to a close call report maybe relating to PPE, or maybe relating to a vegetation issue? You might then have a different set of issues. Is the pipeline question, or is it something subtly different?
Okay, so when we're exploring the data in the database, so like I say, we use the knowledge graph to start the query from. So when we're constructing our query, for example, if we're looking at records related to PPE, then we'll use the PPE node in the knowledge graph to start the query. From there are many different types of PPE. There's gloves, helmets, there's breathing apparatus, even the high-vis clothing that the railway workers wear is considered PPE. All of those are then linked to the PPE node. All of those have many different terms that refer to them. So we start the query from the knowledge graph. So if we're looking for vegetation, we'd be starting the query at a different point in the knowledge graph.
Okay.
We then dig down through the knowledge graph. Is this so what are the different elements, different types of, or different parts of that? So for example, with the nettle, with the plant, we have the stem, we have the leaves, we have, for trees, you have branches, you have trunk. There you may select different nodes in your knowledge graph depending on the query you're looking at. So again, it's an interactive process with the analyst to understand the query, to understand which parts of the knowledge graph correspond to the query. And from there, you then say, now that I've identified the parts of the knowledge graph that are interesting to me, use the automated tools to go and find the records that are connected to those parts of the knowledge graph. There, you have to be careful because, for example, when we're looking at trees, trees have trunks, they have branches, they have leaves. Branches, railway track also has branches, it has branch lines. So you can't use the word branch by itself to be certain that you're talking about a tree. That again is where we want to use proximity within the knowledge graph. If we've got a record that's got the word branch in it, but it's talking about turnouts, points, routes, lines, it's probably talking about a branch line. It's probably not talking about a tree. If it's talking about a tree, if it's talking about foliage, if it's talking about plants, then we've got much higher certainty that the word branch is referring to a part of a tree. Again, wouldn't it be lovely to have an automated tool, a learning tool that knows what's the cutoff threshold? How many other related terms should I be looking for to get 99% confidence that the word branch in this record is referring to the branch of a tree rather than a branch line? Yes, I would love that automated tool. I don't have that automated tool. It would take a lot of training. It would take a lot of examples of case studies of analysts going through and saying, yes, branch in this example does refer to a tree. Branch in this example doesn't. That would take a lot of training time. I can imagine that a learning process, a machine learning process, could be taught with labeled examples and could make reliable inferences following from those. we haven't had that time available to us in our research to do that. If anyone else has got the time to do that in their research, please let me know.
Yeah, okay. So we're running out of time, and I think the last question, which I think leads on quite neatly from that one, is a question from Ryan, where you use an example of 100,000 neurons and the humans have 10 billion. He's suggesting that if Neo4j is used, because that's infinitely scalable, couldn't that solve this problem? But I think the answer you gave there in terms of having that domain expertise is not just about throwing processing power out, it's actually about having the understanding, the knowledge. Is that correct?
Yes, I think so. Yes, so that tool is marketed as being infinitely scalable. I haven't tested them on that claim yet. But yes, even if we were to create a network with that many nodes in there, what do we put in those nodes? How do we populate 100 billion nodes? What process do we go through to populate those nodes in a way so that we get the results we want when we put in a question? We can't just put those nodes in there and hope to get the right results out. We have to put those nodes in there and use some training method to change biases or weights or information or whatever it is you change, so that when you put a query in, you get accurate results out. So yes, we can create that in software, but just having it in software wouldn't be enough. We'd have to have it in software and have some training method for it. And at the moment, I don't know what that training method is.
Yeah, interesting. So, yeah, so I think maybe if the government's next moonshot program was to create artificial intelligence to sort all this out, keep us all gainfully employed for many, many years potentially, but I don't think that's going to happen, unfortunately. Anyway, so Peter, thank you for that presentation. It's been very clear, very informative, very useful. I found it interesting, and I can see there's a lot of it's going to be a lot of development over the coming years, and it'll be interesting to see where this world goes. So thank you very much, Peter. Quick reminder to the audience, the video, once it's processed, will be going up in the BCS member group's YouTube channel. And finally, just a quick reminder that our AGM is lunchtime on the 26th of October. So if you're interested in finding out a little bit more about what we're doing and maybe having a say what we do in the future, then that'll be a good one to join into. So thank you very much. Thank you, Peter. Thank you all for attending.
Thank you.